So, as we have started the chapter Gravitation, okay, from the last lecture, in today's lecture, we will learn the vector form of the law of gravitation. Vector form of the law of gravitation. Okay, you may ask, what is the need of this exactly? Since the term gravitation or gravitational attraction is a force, and force itself a vector quantity, we all know. So we must have a vector form of the law. Okay, to learn this, let us draw the Cartesian system. Okay, axis. Say this is x-axis. You are familiar. This one is y-axis, and this is origin. From there, let it be our usually z-axis. This is the origin having a coordinate 0, 0, 0. Say we have two masses, right? There are two masses over here. One is m1, one is m1, another one is m2, another one is m2. The two mass particles are there located in the space, and their coordinates are say x1, y1 and z1, as well as the second one having a coordinate x2, y2 and z2. If their masses are m1 and m2 as usual. So first of all, we will try to see the position vector. Write down the expression for position vector of the particles. Okay, so let us join this. This one, the line joining the particle from the origin. Okay, this will show its position vector, and let us call it R1. So here we can write down R1 vector, R1 as the expression for position vector of the particle M1 is R1, and R1 is equals to x1 I cap plus y1 j cap plus z1 k. Okay. Similarly, if we want to know the position vector of the particle 2, that is m2 of mass m2, we have to join this by a straight line, and this is straight line pointed towards the particle from the origin. Check the direction. Okay, so this is R2, and the expression for R2 is x2 I cap plus y2 j cap plus z2 k cap. Okay, now see, if R be another vector which joins the two particles, let us consider another vector R, which now joins our two point masses m1 and m2. From the triangle's law of vector addition, what we can write? From triangle's law of addition, yes, what we can write? We can write down, you see, first vector, second vector, third vector in the opposite order is the resultant. So R1, we can write down R1 plus R is equals to R2, or we can write down R is R2 minus R1, or we can write down vector R as R2 minus R1 can be written as x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k. That is what the R. Similarly, in vectors, in the chapter vector, we have learned to write down the magnitude of the vector. So mod of R is under root of what? Yes, x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. And one more thing we know from the vector, that if you want to know the unit radial vector R, that is R cap. So we can write down R cap as, what is the vector? This R cap is written as vector r upon its magnitude, right? Unit vector along the given vector is written in this way, where r cap, the unit vector along the vector r, is equals to the vector divided by its magnitude. So we can write down this expression also from here. This is r, this is node r. You put over there and you can get r cap. Okay, that is another thing. Now see, Newton's law says what? That two mass particles, when they are placed side by side, they are placed at some separation, they attract each other. Okay, so let us see the force acting on M2. Let me write an expression of the force acting on M2 applied by M1. Means we are trying to write down an expression for the force by which M1 is pulling M2 towards itself. Okay, and this force F, since it is attractive, okay, you can see the force F is opposite to the vector R vector. So this force we may name it like this F21, or the force acting on 2 applied by 1. Okay, F21. What does F21 indicate? F21 indicates the force acting on M2, but applied by M. This is the meaning of the expression. If you want to know the reaction of this force, the reaction of the force will be definitely F12. Okay, and in the previous lecture, I have made it clear that F21 should be equals to minus of F12. You have to keep all these facts in mind. F21 should be equals to negative of F12. That means these forces are, what does it indicate? Here is a message, here is a conclusion that these two forces are equal in magnitude as well as they are opposite in direction. They are equal in magnitude as well as they are opposite in direction. Okay, so right now we are trying to write down expression for F21. See F21. F21 is how to write down a vector. To write down a vector, you have to first write down its magnitude and then the unit vector along the given vector, right? So F21 is equals to F21 is, yes, first G. What is G? Universal gravitational constant, G. Then product of the masses, M1 into M. And that is divided by R square of the distance between these two. Okay, R square. Now the forces, is it towards R, along R, or is it opposite to R? Yes, we can see it that this force F21 is opposite to the vector R. So this will be written as minus of R cap, or we can rewrite this as minus of G M1 M2 upon R square into R cap. Okay, since R cap is R upon mod R, right? We may write mod R, okay, or that will be R upon R. We may write without vector sign, the mod R as simply R, okay? So this will be R or R cap, or we can say R is equals to vector R is equals to R into R cap. Very simple, the vector R is its magnitude multiplied by a unit vector along the same vector. This is very common concept, that is a very old concept, we all know that. And so, by replacing this, we can write down the force F21 as. The force F21, we can write down, we can replace R cap. So, R cap is R upon R, right? R cap is R upon R, so what to write? R minus G M1 M2 upon R square into. How is R cap? R vector R upon R, or we can write down this as minus of G M1 M2 by R cube into vector R. बीच का पोर्शन गायब कर देना। F21 is equals to minus G m1 m2 by r cube into vector r. Here, this is a very important thing. There are a question they have asked, okay, that if two particles m1 m2 are there and if F represents the force of interaction between them, this force is proportional to C. The question was given in that form. F with a vector sign overhead, arrow overhead. That means they were asking the vector F. They were not asking you the scalar F, the magnitude of the force. They were asking you the force F. And the question is whether this F is proportional to option A, R, okay, option B, proportional to 1 by R, option C, proportional to 1 by R square, and option D, proportional to 1 by R cube. There is a basic difference between the magnitude and this. If they ask you the same question in some other way, that whether F is proportional to what? To what? R, 1 by R, 1 by R square, and fourth, 1 by R cube. See, there are two separate questions. If you can understand the difference between these two questions. The first question is giving you an expression what? That the force, magnitude of the force, the scalar quantity, right? The magnitude of force is proportional to. Which was the right answer? Definitely, you all will reply the third one is correct. Sir, this is the right answer because this force varies inversely with square of the distance. Okay, but for the next question, you cannot repeat the same answer over here because now you have understood that the vector form, the vector F is not proportional to R square, inversely proportional to R square. This vector is inversely proportional to R cube. So for the second question, these two questions are very close to each other and definitely they are capable enough of misguiding you or confusing you. Okay, so this F is proportional to R, 1 by R square, 1 by R cube. Which is the right answer? Yes, now you all can say, sir, D is the right answer. Okay, thank you. So this is what the basic use. Now see, in some cases, they ask you, so how do they ask the problems? They ask you the problems like this, that two mass particles of different masses given, masses will be given m1 and m2 and their coordinates will be given. Say x is given as -2, 3 and 5. Okay, similarly x2 can be given as -1, 0 and 2. So these are the cases. These two are the coordinates given. So x1, y1, z1 given, x2, y2, z2 given, and then we have to go through this part of the solution to finally get the answer. Okay, so this is the thing. First of all, you are to find out the vector r. Vector r can be found out by subtracting r1 from r2 and write an expression for r. You may go like this. If they ask you the force scalar, that means scalar force means what? It's magnitude only, right? In Newton. Okay, then simply go to the expression F is equals to G m1 m2 by r square. This will be maybe in Newton or whatever, depending on the units given. Okay, so F is equals to G m1 m2 by r square. Okay, simply we put it over there. And how to get r? This r is nothing. This r is what? Actually mod r. And you have learned how to get mod r. But if they ask you the vector form, yes, you have to write down the expression in this way, the final one, and this is the vector form of Newton's law of gravitation. Okay. See, right now we have developed an expression for a pair of mass particles. Right? We are discussing about interaction between two mass particles. But Have you ever thought what will happen or how will you proceed if in a given system the number of particles is more than 2? Okay, number of particles is more than 2. That means for a multi-particle system, right, where the number of particles given is more than 2, they may ask you the force on any of the particles. Okay, let us have a problem. Let us say there are 3 particles placed. Okay, what is a simple question? There are 3 particles we are showing you. Here one, here is the second, and here is the third. The 3 particles are here, and these 3 particles are placed on the 3 vertices of an equilateral triangle. Okay, these particles are having masses. You may call it the masses as m1, or say m, that is twice m, and let it read thrice m. These are the 3 mass particles. Okay, having masses m, twice m, and thrice m. Where, and they are placed on the 3 vertices of an right angle triangle, of an equilateral triangle of each side of length a. Yes. Okay. Now they may ask you, and the 3 vertices are named as A, B, and C. A, B, and C. Okay. Now see, if we concentrate, they ask you the force acting on the charge placed at C or FC. They may ask you the force experienced by the particle placed at C. How to get FC? Okay, this theory is called superposition of forces. We call this topic as superposition. Superposition of forces. Why do we call it superposition? The things will be clear right now. This theory is called superposition of forces. Why? Because the particle at C, you can see the particle C is acted upon by 2 different forces. Why? The particle at A is pulling the particle at C, whereas another particle which is kept at B is also pulling the particle at C. So these 2 are the 2 forces F1 and F2. So the net force experienced by the mass particle at C, the net force F net by the principle of superposition. If n number of forces are acting on a single particle, then the net force F net, F resultant, you may call F net on the particle, right, at C will be F net at C will be, yes, sum total vector sum of these 2 forces F1 plus F2. Okay, so we can find out F1, no problem, and F2, and when these 2 forces be added, take care of the fact that the magnitude of F net you are getting is exactly the magnitude of the resultant vector, the resultant of these 2 forces F1 as well as F2. So we have to use the law of vector addition. Be careful, you are not adding 2 scalars. Don't use 2 plus 3, 5. Before adding, you must be aware of the fact that you are dealing with 2 vectors, 2 or more vectors. So we have to go with the vectors of addition, and since we are adding these 2, right, say the angle between them here is theta, then the mod F or mod of F net will be, yes, under root of F1 square plus F2 square, or mod F1 square mod F2 square plus twice of mod F1 into mod F2, this into cos theta. This is the magnitude of the resultant, and definitely the angle, if I ask the angle what the resultant is making, okay, with one of the vector, say this is the direction of your resultant. For example, this is the direction of F net, and this F net makes an angle, say alpha with F1. Then I can write down to get the direction of the F net as tan alpha, and tan alpha should be written as F2 mod of F2 sine theta divided by F1 mod of F1 plus mod of F2 cos theta. Simple. So F1 F2, the magnitudes of F1 F2 can be found out easily. Okay, so mod of F1 F2 can be found out that much easy because the distance is given A, masses are M and 2M. Let us call them M1 or M2, and this one is M3. Similarly, F1 can be also find out in this way. Okay, and we can find out the result. Another way, the shortcut way of solving such problem, because this kind of exercises can be a bit lengthy. So what we do in case of this kind of symmetrical figures, right? Let us do with another way. So what we do, in spite of doing with this way, we can see one more thing. Let us draw x-axis as well as y-axis, two mutually perpendicular axes. Okay, this is F1 and this one is F2. Yes, and you know well, this one, this axis, the y-axis which I have drawn here, is dividing the angle between, this is the divider of the angle which the two sides of the triangle are making, and we know well, since the triangle in question is an equilateral triangle. Okay, you have to learn these things. When to add two vectors, yes, we can find out the components of these two vectors and then add them. That is easier. So we can find out this F1 here as F1x. Okay, this way F1x, and here is F1 y. Similarly, this is F2. Okay, and this one is F2x, and this one is F2y. Okay, now since F1 and F2x are opposite to each other, you know what to do. The angle to them is 180 degrees, so you have to subtract one from the another, right? And it will be the subtraction of these two. Okay, similarly, since F1y and F2 are in the same direction, you can add them scalarly. So by adding or subtracting them, we can find out the F net along x-axis as well as F net along y-axis. Okay, this will become very easy to find out. Okay, let us have a problem and verify this fact. Apply this. Say we have a triangle like this. This is an right angle triangle. Right angle isosceles triangle. Okay, and the sides are here, say 3 meter and 4 meter. Sorry, 3 meter each. This is a right angle triangle. Say right angle triangle, 3 meter, and another one. This what we are talking about, right angle isosceles triangle. Okay, so two sides must be equal. So let us say this one is 3 meter and this one is also 3 meter. Okay, fine. This is 3, this is also 3, and this triangle is A, B and C. Okay, what to do? And see, it is given that the masses are placed, particles of equal masses. Let us take it easier for those beginners. Let us say this one is M, this mass is M, second one is also M, masses are M and M, right? They may ask you the force acting on any of this. That means they may ask you the force, let the force experienced by the particle at A. That will be easier now. We can use this. So we are just our common sense to which one to be opted. Either directly finding the resultant vector or using the resolution method. Before addition, we have to decide that, and this you will learn it with a lot of practice. When you practice more and more cases, you will learn which one will be suitable in which case. And that will save your time, that will minimize your chance of mistakes, and that will definitely lead you to success. So here, let us see what is the case. Since the particle at A is attracted by these two masses, placed at B as well as C. And these two forces, you see, these two forces are equal, FF. Any doubt? FF. And when two forces mutually perpendicular, two equal mutually perpendicular forces are acted upon, then definitely the F net, so we can say FA, magnitude of the force experienced by the particle at A will be, since masses are similar, that means they differ in no manner, right? They have at equal distances as well as they are equal masses, so both the F will be equal and F net will be written as F root 2. And the angle will be, obviously this angle is going to be 45 degree. Okay? But here we have this. See, you have an equal triangle. See once more. And all these three, again, three equal masses are placed. Three equal masses are placed at the three vertices of an equilateral triangle of each side A. Of each side length A. Okay, and the masses are M, M, and M. Right? And yes, name the triangle A, B, and C. If they ask you the force experienced by either A or B or even C, you can see that. A, B, C. So let us see F at B this time. F at B. Force experienced by the particle placed at B. By at B we mean force experienced or applied to the particle, experienced by the particle at C. Okay, this F represents the force experienced by the particle at B. Okay, how to see? See, the particle at B is attracted by the two particles placed at A and C. Right? So these are the two cases. These are the cases, and obviously here the angles are equal. Angle 60 degree. You can go with this formula also. Okay, and the forces F1 and F2 both are equal in magnitude because the masses are equal, distances are equal, or we can do it in another way. This is say F1, and I can resolve these two along x-axis and y-axis. Yes, I can resolve this. This is our usually x-axis, x dash, and that is our y, and this is our y dash. Okay, this F, this angle is 60 degree, so definitely here the angle is 30 degree. Okay, or even no need, you can do it like that. This is F, so this will be direction of F cos 60, and this will be the direction of F sin 60. Okay, and the force applied by the particle A will also be in the same direction, that is F. So that there are two forces acting along negative x-axis, F cos 60 and F, and there is one force which is along positive y-axis, which is F sin 60, or it will be F root over 3 by 2. And here it will be F plus F by 2, that is 3F by 2. So finally F net, F at B will be, can be written as minus of 3F by 2 I cap plus F root 3 by 2, F root 3 by 2, or root 3 by 2 F, root 3 by 2 F into G. This is the mathematical expression for the F at B. Okay, let's just have one more question. From the chart. This same topic, superposition. Say again, we have an equilateral triangle. Okay, masses are there. Okay, see this time M, another one, and third one. And these are the, what is this? A, B, and C. Okay, and the masses are equal, M, and M. Okay, if the point O, that is centroid of the triangle, that means this is the case, and each side is A. Each side of the equilateral triangle given is A. This is the point here, O, and another mass particle. Another particle of mass twice m. Another particle of mass, say twice m, is placed at the centroid of a triangle. That means this distance, that one, as well as that. That means if this is a centroid, then AO must be equals to BO, and that will also equals to C. Right? So this is the case. Now you know how to get it. Okay? So to get the length, let this length be R. So this all, let it be R. How to get R? This is A, this angle is 60 degree, this is A cos 60, this is A sin 60, and this results in 2:1. Okay, so we can find out the 2/3 of this distance and we can find out the value of R. Once R is known, you see the forces now. Since the forces are forces experienced by a particle at O can be given like this. This is by FA, or the force applied by the particle at A. Similarly, this line shows FB, this vector shows FB, the force applied by the vector at C, B, and similarly we can get one more vector at C. So this is what the force applied by the particle at C, or we represent this force experienced by the particle at O by FC. FC is the force applied by the particle at C, FA, the force applied by the particle at A, and similarly FB is the force applied by the particle at B. Fine. And one more thing, since the masses, these two masses m and twice m, for this pair m and twice m, for this another third pair m and twice m, so that is similar, and all three masses are at equal distance from the particle at O. That means the distances, their distances and their magnitudes or their masses are all equal. That means at magnitude wise equal, right? If I write it magnitude wise, then mod of FA will be equals to mod of FB, and that will also be equals to mod of FC. Simple. Okay? Correct. So because all are equals to G M into twice m multiplied by r square. Okay, which can be easily calculated. Okay, let us see the perpendicular bisection like this. Okay, this angle, this is A, this is 60 degree, this is A cos 60, this is A sin 60, and then divided by the ratio 2:1. Okay, or multiply this by 2 into 2 by 3, and you will get the length up. So FA equals to FB equals to F, this is J, this is that. Now see how to get the F net by the particle at O. Yes, here since there are three vectors, more than two, the resultant formula is for 2. Okay. Either you apply the resultant formula for two of them, get the third, the resultant, and then resultant should be added with the third. Okay, but that will be quite lengthy and a bit complicated, and that will nothing else but this will attract mistakes. Okay, silly mistakes I say. So easiest way is what? To draw the coordinate axis over here. Yes, this is our x-axis. That means we are going to apply which one? The resolution formula. Yes, we will resolve these vectors, okay, in terms of their components along x-axis as well as along y-axis. Fine. Okay. So that is very simple. This angle as usual 30 degree, that is also 30 degree. Right? This angle and these two angles are equal. So this is 30 degree, 630, that is also 30, and this F1 we have F1x. Over here, FA along x-axis, and here we have FA along y-axis. Similarly, FB we have FB along x-axis here, and we will have FB along y-axis here. Right? So these are the forces, but since FA and FB are equal in magnitude, but here we can see their components, x components, right? They are also equal in magnitude. Fax mod of Fax is equals to mod of Fbx, right? And what we see, since they are equal in magnitude, they are opposite direction, what we can write down? F vector Fax is equals to minus of Fbx. And if we do that, then the net force along x-axis will be F net along x-axis, F net along x-axis, F net along x-axis can be given by Fax plus Fbx. Since Fax is equals to minus Fbx, we know well this result is going to be 0. That means no horizontal force will be experienced by this one. Okay. Similarly, Fa and Fb, sorry, their y components, Fay, Fby, this is Fa, this angle is there Fa, and this is cos theta, this sin theta. It's okay, sin 30 degree, 1 by 2, 1 by 2. So Fby is what? Fby, as we can see, Fby, mod Fby is F by 2. Okay, is Fby is equals to Fb by 2. Similarly, Fc along y, Fcy mod will be Fc by 2. Okay, mod of Fb by 2, mod Fc by 2. Simple. These two are equal. Since these two are all, these are equal, their magnitudes are equal, that means these two are equal also. And together, if we add them, this will become equals to Fc. So Fc is upward and the sum of these two is downward. That is what we can say F net, or we can say F net along y-axis will also be 0, right? That means the point by the particle, even it is of double mass, twice m, it is unable to experience a gravitational force. Right? It means the centroid of this in this particular case, the centroid is right, is a point where whatever mass you give, however large it may be, however small it may be, but this particle kept at O will experience no force, or F net at O will be 0. Right? That gives rise to another problem, another type of conception. The point where even in presence of multiple mass particles, right, if there is a point lying in the space where there is no effect of gravitation, that means this whatever mass you put over there, if you keep any mass over there, it will not experience any gravitational force. Such points are called null point. Null point. Yes. A new concept. And they ask you, it has happened so many times, they have asked so many times in competitions, they have asked to locate the null point of a system of mass particles. So you must know first what is the meaning of the term null point. I think you have got it. Here the point O itself is what? Is a null point. Okay. Null point, as you have discussed. Null point is what? So null point can be defined as a point where F net gravitational force or any kind of force, right? F net is 0. Even there is a presence of any number of particles, right? But if you put a particle at this particular point, it will not experience any force. Okay, so for practice, let us have a question like this. Say we have two particles. Okay, it is given. Here are two particles given. Suppose. Okay, one and the another one. Okay, and they are of masses. They are of a distance. Say 5d. 5d is the distance between them, whereas their masses are m and twice m. Okay, their masses are 1 and m and twice m. Right, they are separated by a distance 5d. They may ask you, locate the null point of this combination. Which point is the null point? Okay, or whatever, where is the location of this point? Locate the point. Or how far is it from the particle at A, or even, or from a particle at B? Very simple. Let us suppose. Now since if a particle is placed over there, the force is directly proportional to the product of the masses, and it should be inversely proportional to the square of the distance. Okay, since this is the force applied by we are not dealing right now, we are not the small element of the rod and the point particle given, the point mass given. So the force is also an elementary force dF. This is what? dF. And what is dF? What is dF here? dF is what? Obviously now we can, since I have told you, since the element we have taken is very small, we can now easily use it as a point mass. So there is a formula, for calculating the interaction between the point masses, and that expression gives you what? Like this, F is equals to G small m into dm, m1 into m2 upon r square. This is what? R square. Okay. So r square, we can put it over here. Now, putting the value for the force due to the whole rod will be obtained by integrating both sides. And if I integrate this like this, dF is equals to G small m. Okay, and dm, what is dm? Lambda dr. So this will be lambda into dr upon r square, right? Lambda dr, and in the denominator is dr square, or we can further write is at G small m into lambda, or lambda G small m into, since lambda is constant, right? It is not integrable, so we have to take it out. G lambda G m small m into dr upon r square, right? And see, r is the distance between the element and the point mass. Okay, but this is not the case of a single element, right? You can check where you can see it easily that this kind of, I have told you, this kind of elements arranged in a linear way on a line, they make the whole rod, and that means the first element over here will be at a distance d. So the initial value of r is d. Okay, d, and then the last element resides at a. Rod is not beyond a, so it ends at a. So the maximum value of r, the closest element of the rod will be at d, and the farthest element of the rod is at d plus l. Correct? This is at d plus l. So what? D and d plus l. Okay, the rest is easy. So we can find the integration of this will be f, or we can write f is equals to, or f is equals to lambda G small m into integration of r to the power r square, or obviously we know well the integration, integration of dr by r square will be r to the power minus 2 plus 1 upon minus 2 plus 1, it will be minus of 1 upon r, minus of 1 upon r. Okay, so it will be minus of 1 upon r, limits d to d plus l, putting the value upper limit, lower limit, finally put the value of lambda as m by l. We can write down m g m small m upon l, and this will be upper limit minus, okay, minus upper limit minus lower limit. So minus of 1 upon d plus l, and minus into minus plus 1 upon d. Okay, or this will be written as g m by l. This will be 1 upon d minus 1 upon d plus l. This is the expression for the force applied by the rod on the point mass. Okay. See one more case, just for a practice, so that you can become easy, compatible with such situations. This because this kind of things we usually ask. Say, I have a wire. Let us have a wire. I have a wire of mass m and length l. But this wire is not kept straight. The wire has been bent. This wire has been bent to form a semicircle. This wire of length L is bent to form a semicircle, and a point mass is placed at the center of the circle. Okay? And a point mass is placed at the center of the circle. Okay? And this point mass having a mass capital M. Okay? Small m, sorry, small m. Okay? The rod having a mass M. They will ask you the force experienced by the point mass placed at the center of the half ring. Okay, this is a ring, half ring. This wire of length L was bent like this. Okay, it is easy to understand. So, what is the first of all we have to find out the radius. Okay, what is the radius of the ring? Yes, dear, you can write down it easily. It is a ring. Total length. Let it be R. Let the ring's radius be R. Yes, then the total length A to B. This circumference, saying half of the ring, half of the whole circumference, right? Okay, it will be pi into R. So total circumference is 2 pi R. Half of this is pi R, and pi R is equals to L, or R is equals to L upon pi. Okay, equation number 1. Okay, this is there. Now we will consider one. Now again, since it is not possible to apply laws of Newton's law of gravitation, okay, in its real form over here, so we have to do what? Again, we have to go with the element form. Okay, and then what to do? What a simple thing. Take a small length element over here, like this. Okay, we have taken a very small part of the which is of like this, okay, which is like this. So case is very simple to understand. Okay, let us take a small element over here, right? And this is small element. I'm just marking by red color. You can understand this part of the ring. And say if this subtends an angle theta from the x-axis, right? Theta. And this element subtends an angle d theta. Yes. So this case is like that. There is an arc. There is an arc which subtends an angle d theta, and radius of the arc is r. Then length of the arc AB. Length of the arc AB d can be written as r d theta. We know well. So length of this arc is also r d theta. Okay. Now see, it is actually the rod, the wire that has been bent to make a half ring. That means, okay, this is the length. So its mass will be, if they ask you must know this mass of the element. Otherwise, you can't apply it in the law, in the formula. So dm will be, how to get dm? Dm will be here m by L. Dm is m by L into dm by L into mass by linear mass density into length of the element into r d theta, or we can write down this as m by L into what is r? L by pi. This into d theta, L will cancel, and we finally write down m d theta m by pi into d theta. That is what exactly? Dm, mass of the element. Or we may call it write down d capital D. Okay, fine. So this is what? The mass of the element over there. Now we are in a position, okay, to apply the law directly. Why? Because this very small element, this infinitesimally small element
can now be treated as a point mass. If I can treat it as a point mass, right, I can write down the force, right? So the force will be, obviously the force will be like this. This will be D. Okay, because take care, always keep your mind alert that gravitational force is a force of attraction, not repulsion. So always attraction is there. dF will be radially inwards. Okay, and this dF will be how much? dF will be written very easily. G small m, mass of this particle that is placed at the center, into mass of this element, dm, upon the distance, that is r square. That is r square. Okay. Now by integrating both sides, I can find out finally f. Okay. So check it. What is this? This force is there. df. df is there, but that things are not that much easy here, because there are so many variables. One, you can see when we go like this, right? It is what? Theta is variable. Theta is also a variable. So this is d theta df, and I have to resolve now df also along its components, right? One, here it is df along x-axis, and another one I will resolve it along the y-axis, and that will be like this. This is df y. That is called symmetry check. Since the y-axis is the line of symmetry of the half ring. Okay, so if I take such an element, because the rod is, I have told you in the previous problem that the rod is supposed to be made up of large number, infinite number of such small elements. Okay, so definitely the elements of the rod will not be on this side only, they will be on the other side also. So let us consider an identical element like this. Okay, over here. This will do what? This will also attract the force like this, the body like this. And if this will attract, we can resolve it along x-axis and y-axis as usually. So there will be another element, another component over here, and this will be minus dfx. Okay, or there will be dfx in the opposite side. Since these two are equal and opposite, they will cancel out each other. That simply means the net force experienced by the particle at the center should be along y-axis, not along x-axis. Why not along x-axis? The reason is very simple, because every element on the right side has a counter element on the left side, and these do what? Yes, its component on the x-axis will cancel the component of the second identical part on the other side. So there will be no force along x-axis, or we can say integration of dx will be dfx will be 0, but the only force that exists will be dfy. And since this df, what is dfy? dfy is nothing but df sine theta. dfy will be df sine theta. So df is here, put it over there, and df is g small m upon r square into dm. What is dm? Into capital M, and by pi into d theta into sine theta. So this is what? Sine theta into d theta. Fine. Okay, r, we can replace r, as r was not given. Later on we'll do it. Okay, so this will be finally an integration of this will give you f net on this point mass small m. Integration of dfy. Don't integrate dfx. Why? You can check the symmetry before going to the detail. You can't do it here, right? So exactly the things are like this. Here dfx is 0. Why? Because the x component of the force due to an element on the right side of the ring, the y-axis, will be cancelled out by its counterpart on the left hand side of the y-axis. So finally we have to integrate that one. So here it is have gm by this. So we can take all these factors g by into r square integration of sine theta d theta. Okay, now just we have to be a bit careful before setting up the, since this is a definite integration, we have to first be careful in setting the limits. Which one is the lower limit and which one is the upper limit, right? Means what? From where the theta starts. Theta starts from here. And that gives you the first element of the ring. When theta is 0, you get the first element at A. When theta is 180 degree, you get the last element, that is at B. That means the range of integration is, the limits of integration is theta equals to 0 degree to theta is equals to pi or 180 degree. Okay. Integration of sine theta, you know. Integration of sine theta is equals to minus cos theta plus. Right here, it is a definite integration. There is no need of this, so it will be g m upon pi into r square, and that will lead to minus of cos theta. Theta is 0 to pi. Okay, putting the limits g m by pi r square, and that will be minus cos pi, minus of cos pi, minus plus cos 0 degree, and we know well cos pi is minus 1, cos 180 degree is minus 1, and minus 1 into minus will be plus 1, cos 0 is also 1, so finally we get it twice g m upon pi smaller square. Okay, so since we have seen the f at O is twice g m by pi into small r square. Since small r was not a part of the main question, we have to replace the small r from here, and small r is equals to L by pi. So replacing, putting r is equals to L by pi, we can find out the answer FO in terms of the quantities given. Okay, that is the problem and that is the solution. So there are so many things and there are so many applications also. They may confuse you, okay, by adding other forces along with the gravitation, like buoyancy and so. But this is the situation over here, and see the case. In some cases, this time you have learned the application of gravitational force, the laws of gravitation, basic laws of gravitation. But in the beginning, the formula. But in the beginning, we have mentioned that the force, as you have seen also, that this force is for the interaction between 2 point masses, right, who are separated by distance r. That means these forces are active. These forces are effective even from a distance. It need not to be, the bodies need not to be in the close contact of each other. They can attract each other even from a distance. Right? That means what? This force is not a force in contact. Okay? And since it is not a force in contact, otherwise field forces. This is the field forces. The gravitational force is a field force. Field force means every mass particle, okay, every mass particle will create its own region of influence, and anyone else, if it gets spotted over here in this region of influence, right, it will be pulled by the particle. Okay, say this is particle capital M and another particle of mass small m is spotted at somewhere at some more distance, okay, from capital M. Yes, it will start responding, it will start feeling attracted. Okay, yes. The question is, how does capital M interact with small m even when they are not in contact? Yes, the answer to this query is by creating a region of influence, and this regional space, region in which its influence works. Field of forces. We may call it field of forces. Yes. Okay. Okay, since this is the case of gravitational interaction, the field we will call it now as gravitational field. Gravitational field. Okay, say here is a point mass, capital F, placed at point O. Okay, and if you want to check what is the strength of the field, what is the intensity of its gravitational field at a distance, say small r from it. Yes, if you are able to know, if you are interested in calculating, knowing the strength of the field at somewhat distance r from the mother charge, mother mass, right? So if you want to measure it, no problem. You have to put a, how to test whether there is a field or not. If any point mass placed at any point near it, and if it is feeling attracted, then definitely there is a field. Okay. So this attraction is a guarantee of presence of field. Clear? So this will be the case. Now see how to measure the field. The strength of the field at A is known as Eg. Eg at P. We write it like this. E gravitational at P is defined as the force experienced by the particle at P. Okay, force experienced by the particle at P, force experienced by particle by F by small m divided by, or force experienced by particle at P, F upon mass of the particle small m. This is force per unit mass. Okay, this m is the mass of this particle. Since this particle mass, this point mass is used to measure the or check the existence of the gravitational field, or it is used in measuring the intensity of the gravitational field, the strength of the gravitational field that has been produced by capital M. So this is used to call, we also call it test mass. This is a test mass. Okay, why is it called test mass? It is called test mass as it is used to measure the intensity, and intensity of the gravitational field at the location of test mass, that is at the point P, is given by the force F, which force experienced by test mass divided by mass of the test mass. Okay, since it is force by mass itself is a scalar quantity, force is a vector quantity, one should be very much sure that the field is also a vector quantity. And since it is a vector quantity, yes, it should be treated like force, like other vectors. And since it is a vector over here, we can't use it like a scalar. At the same time, we must remember that it will have a magnitude as well as a particular direction. So the direction and magnitude can be written since F is equals to what? Minus G M upon R cube into R. Right? If you remember, we have done this previously. This is the force F. Then what is the expression for gravitational field due to the point mass at P? So E gravitational at P is given by this F divided by M, or we will write down minus G M by M upon R cube, this into R, or this can be written as minus of G M by R square into R cap. Okay, G M by R square into R cap. This A is there, that is E G at P is F by M minus G M by R cube R. This is what the case is. So this is how we write the gravitational field, and this gravitational field having a unit, since it is force divided by mass, unit should be Newton per kg. It should be written as Newton per kg. Okay. And these things are almost similar. In this case, obviously, in case of multiple fields, due to multiple type of bodies, yes, we can use use it like vectors and rest of things are almost similar. They may ask you the field at a point due to a rod and so and so. Okay, so these things are almost similar. They may ask you a rod, right? They may ask you like this. This is problem G. Here is a rod, okay, of length L, mass M as usual. One end is A, other end is B. Here is a point P. This point P lies on the perpendicular bisector of the. Okay, the point P lies on the perpendicular bisector of the rod, and they ask you the gravitational field strength. What is the strength of the gravitational field E gravitational at P due to the rod? Yes, we have to use it like this. See, there are cases like this. Fine. So let us take one end. You have to consider one element. Fine. Anyone on the rod? Yes. This will have the field over there. Join it like this. Okay. This will have the field or in this way. That is what DE. And DE can be resolved. Now DE must be resolved, one along x-axis, other along y-axis. Yes, this is DEY and this will be DEX. Fine, DEX. Similarly, now just note, this is not the answer, complete one, right? This is what? One part, one element. Obviously, this is the midpoint of the rod O, and OP is the, as I said, OP is a perpendicular bisector of the rod. There may be unsymmetrically other elements, right? Yes. The other side, lower half, and that too will be written like this. This angle may be theta, and this will be DE. This DE will have x component and as well as y component. So, what is the benefit of using symmetry? You can check easily that there is no component of the field along y-axis, as each component on y-axis due to one element, one symmetrical element on one half, and it will be cancelled out by the same element taken on the next half. Okay, so DEY, or we can say integration of DEY, net DEY will be 0. So what will exist? Only DEX. And DEX can be found out right now easily. Okay, here is a distance. See, let this be R, right? And this length is given, suppose D. Okay, and let it be Y, and this length be dy. Length of the element be dy. Okay, it is taken like this. Once it is there, one thing is clear from Pythagoras, R is equals to R square is equals to, what is R square? You can check, it is D square plus Y square. D square plus Y square. And mass of the element, this one, dm will be, come on, what is the mass of the element dm? M by L, mass per unit length into length of the element. That is what the expression for dm. Since this is dm and here the point B, the field expression for field will be dE. dE will be how much? Minus G dm upon R square. Fine. Later on, by putting all these things, resolving them into components along x-axis d cos theta, and for that you have to resolve it like this. Set this end and that end. Okay, and take care. If you are doing that, your theta is positive. Okay, theta is here like this, and this one is opposite. So I have to take this one and with this, and that one like this. Fine. This is the case of that. Plus theta minus theta. Yes, you can put it easily, and we can find out since these two are equal in the case. Okay, the things are simple to do. Okay, does this today, right? So I have given you a problem. I have given you certain hints how to start. I have given you a start. Okay, so that you can frame the problem, you can think the problem, and then it's up to you now. Okay, to solve this problem and get us answer of this. If you can do, it's better. I I will happiest man on this universe. But if you fail to do, if you fail to get any topic and any problem, right, any trouble, then in the next video I will give you its solution. Okay, thank you.